Okay, good morning and thank you very much for coming to my talk. My name is David. I'm a Go programmer from Sydney. I'm delighted to be here to talk about Go. Finally, I do a lot of travel, and finally talk about Go inside Australia. So very happy to be able to do that. This talk is called Solid Go Design, but it's very difficult to follow someone like Dave Thomas. And compared to the other speakers who you're going to see today, I feel with so much experience, I feel like a bit of an interloper. So hopefully you'll take it easy on me. So for the people in this room, who's tried Go? Who's used Go? Oh, this is good. Okay. Now, keep your hand up if you've actually written some Go. Yes, good. And keep your hand up if you've deployed a Go application in production. Okay. Only one? Okay. All right, we'll talk later. So my own interest in Go was sparked in 2009 by the language's fresh approach to the problems of large-scale software development. I think Go represents, it's a member of a triumvirate of three modern languages, including Rust and Swift, that represent a return to a model of programs that are compiled directly to machine code. So Go is memory safe, it's concurrent, and it's without a requirement to have a virtual machine or an interpreter. And I think this has been one of the reasons for its success. And all three of these languages represent a movement away from this everything is an object paradigm that's been the mainstream narrative for quite a long time. Now, Go is also a young language. We had the 4th birthday announcement of the 1.0 release about a month ago. I mean, we've had 7. We're working on our 7th minor point release so far in the last, and that's been represented about the last 4 or 5 years. So we're still quite young. We still have a long way to go. And Go is also not an academic language. It's a language that's explicitly designed for programming, we say, in the large. And it's influenced heavily by the needs of its patron, Google. And so I think that Go is a language that's designed primarily for groups of programmers, for the productivity of programmers in plural. Now, for my day job, I work on 2 large Go projects. The first is the Go language itself, and the second is Juju from Canonical, my employer, who are very generous to send me here today. One aspect of dealing with projects, maybe you think these are big, maybe you think they're small, but one aspect of dealing with projects of this size is that I think there's more to argue about than just the name of variables and file layouts and how many spaces are the correct number of spaces to follow the period. But I don't mean to imply that design is not important for smaller programs. I mean, personally, I think that we should all be trying to write smaller programs. But sometimes in the world of commercial development, it's not compatible with this idealistic worldview. So design is important for programs of all size. But I think it's most important when the size and the age of your program grows. That's when the design becomes paramount. And authors like Sandy Metz, Robert Martin, and the late Jim Weirich remind us that the only constant in software development is change. And so to believe in a world where software is done completely is to believe in a fantasy. So in his book, Agile Software Development Principles, Patterns, and Practices, Robert Martin introduces a series of ideas for the construction of software that is amenable to change. Now, Martin's software solid principles are closely associated with object-oriented languages of their time, C++ mainly, and then Java and C#. And although they span different eras, these languages all share the same class-structured, inheritance-based foundation. So this talk focuses on the interpretation of Go programs according to Martin's solid principles. It's not a theological deconstruction of solid. In effect, I hold these principles to be self-evident as good ideas, and hopefully by your presence here today, you agree with me to some degree. So in the introduction to their book last year, Alan Donovan and Brian Kernighan wrote that the Go project includes the language itself, its tools and standard library, and last but not least, a cultural agenda of radical simplicity. And a sign of this drive towards simplicity is Go's abandonment of a traditional class-based inheritance. In fact, Go supports no form of inheritance whatsoever, and instead commits the language firmly to the paradigm of composition. So does this mean that Go programs are not object-oriented? And does this mean that Go programs cannot or do not follow solid design principles? And this is really what we're here today to look at. And of course, if we're talking about solid, we start with the S, which stands for the single responsibility principle. It's obviously the most well-known. And the single responsibility principle states that a class should have one and only one reason to change. But why is this important, that as a unit, a piece of code should only have one reason to change, one impetus to change? Why should we care? Like, why should we, as programmers, care about this level of taxonomy? I mean, to me, as distressing as it may be, the idea that I might have to change my own code, it's certainly far more distressing that the code that my code depends on might change underfoot. So when your code does change, it should be in response to direct stimuli. Your code shouldn't be the victim of collateral damage. And two pieces of code that are highly sensitive to change in their counterparts, we can say that they're tightly coupled. And coupling is just a word that describes two things which change together. A change in one induces a change in the other. So code that has fewer responsibilities has fewer reasons to change. So Uncle Bob's imperatively styled single responsibility principle is derived from Tom DeMarco's older definition of cohesion. And as DeMarco puts forward, cohesion is a measure of the strength of the association between elements inside a module. A highly cohesive module is a collection of statements and data items that should be related as a whole, because they are so closely related. And any attempt to divide them would only result in increased coupling and decreased reliability. So in this context, the word cohesion is describing the property of two bits of code that are naturally attracted to each other. I mean, they stick together like the poles of magnets. And to describe the units of coupling and cohesion in Go programs, we might talk about functions and methods. I mean, this is very, very common when we're talking about the single responsibility principle. But in truth, it starts with the Go package model. Go packages are composed of various elements, constants, variables, types, functions, and methods. And each of these are either public or private, or, if you like, they're exported or not exported. And true to Go's focus on simplicity, everything in a package is by default private, unless the identifier starts with an uppercase letter. So all Go code lives in a package, even the main function, which we call, not particularly inventively, the main package. And a well-designed package starts with its name, which is both a description of its role, its purpose, and a namespace prefix. And some examples of good packages from the Go standard library might be the HTTP package, which obviously provides a client and a server. The exec package, which executes things. And unfortunately for me, the JSON package, which is a poor example. So when you use another package's symbols inside your own package, this is accomplished with the import declaration. And this establishes source-level dependency, or perhaps a coupling, between two packages. And once imported, the symbols of that package always are prefixed with the package's name. And this makes it really easy to figure out where an identifier is declared, like where did this come from? So this small but completely functional microservice tells people the time. Is everything here to run a web server on port 9001, We register a route on the time, and we serve as many clients as connect to it. And this uses the services of 5 other packages from networking, HTTP, string formatting, time, and logging. And the purpose of each of these packages is basically self-evident. It's right there in their name, with the possible exception of funct, which is our homage to Plan 9. And this is also a good example of how type inference works in Go. Go is a statically typed language, yet the program contains only one type declaration, right here in this route for the time handler. But this is still a completely statically typed program. And this focus on names is not just noun pedantry. A poorly named package misses the opportunity to enumerate a purpose, and that's assuming it has one. I mean, from its name, what does the server package do? Probably serves things. But what? HTTP? FTP? SCP? Who knows? What is the purpose of a private package? Like, what does that provide to people? Things that I shouldn't see? Common is really a reaction to having a server package, because if you have a server package, you'll have to have a client package, and you'll have to have a third package that has bits that are neither server nor client. And the utils package, a complete anti-pattern. It becomes a catch-all for a dumping ground. And utils packages, apart from having no clear purpose, they change frequently and without real cause. And I don't think a discussion of Go, or decoupled in design in general, could be complete without talking about Doug McIlroy. In 1964, Doug McIlroy postulated about the power of pipes for composing programs. And his observation really became the foundation for what is accepted to be the Unix philosophy. Small, sharp tools that are combined that solve larger problems, problems perhaps the original author had never intended or had never envisaged. So personally, I think that Go packages embody this idea of the Unix philosophy. In effect, each package is a small Go program. It has access to all of the language. And just like programming with the Unix shell, Go programs can be composed by combining together a loose collection of packages. The second principle is O for the open-close principle. And this comes from Bertrand Meyer's 1988 book, The Object-Oriented Software Construction. And its reinterpretation in Solid states that classes should be open for extension, but closed for modification. Now, Go doesn't have classes, but we do have types, and we have methods on types. So in this example, we have a structure. It's just got a single field called v. It's an integer. And the type A also has a method called value, which just returns the internals of v. Nothing particularly special there. We also introduce a type B using this syntax, which shares the same underlying type as A. Now, this is important because B doesn't extend from A. Like this is not inheritance, and nor is B derived from A. What's happening here is both A and B share the same underlying type, this structure with one integer field. But that's all they share. Because they share the same underlying type, values of type A can be converted to type B with this syntax, because ultimately they share the same layout in memory. They look the same in memory. But the method set of B will be distinct from the method set of A, because although they share the same underlying type, the methods are associated only with the type on which they are declared. So here we see A prints out 100, B, which we saw earlier, shares the same underlying type, But the method set of B is empty because value is only declared on this A type. If we want one type to have access to another's methods, we can instead do something like this. And in this example, similar to the last one, we have type A. It's got a year field, and it's got a method on it called greet, which prints out a salutation for the year. We can use this syntax here, where A is a field inside B, and we call this embedding. And that gives, so the callers of B will see B's methods, because B has another greet method, overlaid on A's. But embedding isn't just for methods. It also provides access to the embedded types field. So we can see that A has a year field, and B has a year field because it's inherited it, not inherited, it's accessing the embedded field from A. So embedding allows Go's types to be open for extension. In this counterexample, we have a cat type, has a name, and has a method that returns the number of legs, which is the average number of legs for cats. Now we can embed this cat type into a new type, which we're going to call an octocat, and declare that octocats have 8 legs. Now, although octocat defines its own leg method, you can see it here, second from the bottom there, which prints out 8, as we expect. When we call the print leg method, it returns 4. It returns the original 4. And this is because print legs is declared on the cat. And so the value it takes as its receiver is a cat. And so it's delegating to the cat's leg method. So values of cat embedded in any type are completely unaware that they're being embedded. So their method set cannot be altered. And thus we can say that Go's types are closed for modification. And this is not a wacky form of inheritance. There is no implicit this parameter in Go's methods. In truth, methods in Go are little more than syntactic sugar for a function with their receiver, with the first parameter, which is their receiver. And so the receiver is exactly what we pass into it, the first parameter of the function. And because Go does not support function overloading, octocats will never be substitutable for regular cats. And because we're talking about substitution, that brings us on to the next principle. Coined in 1988 by Barbara Liskov, the Liskov substitution principle states, roughly, that 2 types are substitutable if they exhibit behavior such that the caller is unable to tell the difference. Now, in class-based languages, the Liskov substitution principle is commonly interpreted as a specification for an abstract-based class and various concrete implementations. But Go doesn't have classes, nor do we have inheritance, as we saw. So substitution can't be implemented in terms of an abstract class hierarchy. Substitution is the purview of interfaces in Go. In Go, a type is not required to nominate either by an implements declaration on its type or by extending some form of abstract type that they implement a particular interface. Instead, any type that can implement an interface provided it has a signature which matches the interface declaration. And while it's not possible to modify a type from another package, at any time a new interface might be defined, and if a type satisfies this new interface, if it has all the methods that match that interface. So we say that in Go, interfaces are satisfied implicitly rather than explicitly. You don't have to nominate that you choose to nominate these interfaces, you just do. And this has a profound impact of how interfaces are used in the language. A well-designed interface is generally a small interface. The prevailing idiom is that interfaces generally contain only one method. And it follows logically that a small interface will lead to a simple implementation because it's relatively hard to do anything otherwise. And so this leads to packages which are comprised of simple implementations connected by common behavior. And a canonical example of small interfaces comes to us from the IO package. These are the three kind of canonical stream-orientated interfaces in Go. Read, which takes a buffer of bytes and returns to you how many bytes it actually read, like how much of that buffer it used, and possibly an error. Write, which does the inverse. It takes a buffer and tells you how much it wrote to the underlying stream, and possibly an error. And generally, writes are either fully satisfied or they fail. So it's unusual that you will not write all of the data successfully. And closer, because we're generally dealing with things that are resources, file descriptors, network connections, things that take physical resource, close is very important as well because it's a signal that no more processing will be done. And these interfaces are highly pervasive inside Go programs, mainly because of their simple contract. Like there's just one method for each of them. For some examples, we have the multi-reader, which takes a set of readers, a variable number of readers, and returns to you a new reader whose result will be reading each of those underlying readers in turn, just concatenating their result. The limit reader takes a reader and returns to you a new reader, which will register end of file, regardless of what the underlying one said, after a certain number of bytes. So you can place that over an existing reader to say, I just want to read the header, like many protocols say, there's this much header and this much body. So you can, rather than reading that data in and kind of keeping it off to the side, you can just create a new reader which will say, I don't want to read further than that. A T-reader is analogous to our T command in Unix. It takes a reader and returns a reader that has a side effect of anything read through it will also be written to the supplied writer. So that lets you peek into the operations of a read. Further afield, we have functions which create readers on strings and bytes. So you can move from this world of materialized in-memory data to treating it like a string, And bytes.buffer, which is a very popular in-memory implementation of both a reader and a writer. So we create a bytes.buffer. We don't need to initialize it. The 0 value is good enough. We can write to it some bytes. We can use it as a sink for formatted printing. And then we can pass it to io.copy, which takes a reader and a writer and reads everything from this reader and writes it to the writer. So bytes.buffer can be used in both these roles. It's a source and a sink. Now, Go doesn't have IFLs designed by contract, but we do have this tradition of small interfaces. And so the Liskov substitution principle could be just summarized in Go by this lovely aphorism from Jim Weirich, which is require no more and promise no less. And this provides a good segue to the fourth of the solid principles, which is the interface segregation principle. The interface segregation principle states that clients should not be forced to depend on methods they don't use. In Go, the application of the interface segregation principle can refer to a process of isolating the behavior required for a particular function to do its job. And for a concrete example, say I've been given a task to write a function that just persists data to disk, like some document, some config file. The job is to persist the data to disk. Look reasonable? I mean, we don't need to worry about the implementation. We'll just look at the signature. So I could specify this function to take an OS file, which is from the standard library, and represents file-like things. But it certainly has a few problems. I mean, the signature of save, as I've written it, really precludes the option to write data to a network device. Unless, of course, that network has been created, like mounted, like a network share or something like that. It can't send the data to a web server, we can't write it to a tar file, can't do anything like that. And it's probably likely that network storage is going to be a requirement pretty soon. And that means that to fix this problem, we have to do one of two things. We'd either have to change the signature of this function, or worse, make a new one, save to network, save to tar file. And save is also unpleasant to test, because it assumes that the host this code is running on has a disk to write to. And this might seem a little bit far-fetched, but in this kind of Docker world, like not having a writable disk is actually a thing that's going to happen. And because this function works with files, to actually test how it works, I have to run it, and then I have to go and read the file that it wrote to. And I have to make sure that the file is written to a new temporary location every time, and I have to make sure that it was removed afterwards so I don't waste space on the build server. So, a whole bunch of problems. Also, os.file defines a lot of methods which are not relevant to save. Like, it can read directories, it can tell you if paths are symbolic links, it can change modes, it can do a whole bunch of things which save is not interested in. So it would be really useful if the signature of the save function could describe only the parts of OS file that we care about. Now, in Go, we often compose interfaces from smaller ones. So this is again from package IO, and this form, as we saw similar with embedding, we can compose a larger interface by embedding 3 smaller ones inside that. So we could use this read-write-closer interface to improve save. So, not surprisingly, we changed it to take a read-write-closer. And this makes save both broader in its operation. It clarifies both to the caller and me, the author of save, the things that I'm actually going to be doing, the things that I care about that OS file used to provide. As the author of save, I can't check a directory. I can't test if this file is a symlink. I can't do any of these things because the implementation of OS file has been hidden behind this interface. But we can probably take this a little bit further and improve it a bit further. I mean, firstly, it's likely that save is not going to read the file it just wrote. I mean, if it follows the single responsibility principle, it will be responsible for writing files. The job of reading and verifying a file is probably going to be somebody else's job. So we can narrow the specification for save to just talk about writing and closing. Like we've said, it doesn't need to bother about reading. It's never going to read anything from this. It's just going to write to it. And second, by providing save with a mechanism to close its stream, which we inherited kind of as a side effect of wanting to look like filed-like things, I think this has created a bit of an ambiguity. So save can take a thing you can write to and can close. So under what circumstances is it going to close? Who knows? Maybe it always closes. Maybe it only closes when there is an error. Maybe it always closes when there is not an error. Who knows? I mean, that's maybe something you'd put in the documentation, but it's an ambiguity. And it's a problem because as the caller of save, I might want to use this stream for something else. Like I might be streaming one document and another and another and another, and that's going to break if save unconditionally calls close. So a crude solution would be to define a new type that embeds a writer and provides a close method that does nothing. So we can pass this, because this now has write from the writer and close, it will fit that writer-closer interface. That's one way we could do it. I don't know if this is a violation of the substitution principle, but it's probably not the best because, I mean, we've broken the contract. Close actually now does nothing. So we can probably do better than that by changing the interface for save to be even tighter. So now save just takes a writer, and its job is just to write that document out, just to serialize it to that writer. And so by applying this interface segregation principle to save, the result has simultaneously been a function which is very specific in what it does. It only writes to the writer. And it's also completely generic in what it does because it can write to any writer that you have, being a file on disk, being a byte buffer that we saw before, some network stream. It doesn't care. And the final solid principle is, of course, dependency inversion. And the dependency inversion principle states that you should depend on abstractions and not on concretions. So what is a concretion, and how does one invert one's dependency upon it? And more importantly, what does dependency inversion mean in practice to Go programmers? I mean, we're certainly not talking about dependency injection and dependency injection frameworks. At a basic level, if a concrete type is a concretion, then an abstraction would be an interface. But more fundamentally, a concretion is one piece of code depending on another. Now, if you've applied all the principles that we've talked about up to this point, your code should be well factored into discrete packages, each of those packages having a single responsibility or purpose. Your code should also be describing its dependencies in terms of interfaces. And those interfaces should be well factored to describe only the requirements for that particular function. So, in other words, there shouldn't be a lot to do here. So maybe it's useful to look at a slightly longer version of the dependency inversion principle. And that is that high-level modules should not depend on low-level modules. Both should depend on abstractions. And abstractions should not depend on the details. Details should depend on abstractions. So what I think Uncle Bob is talking about here, certainly in the context of Go, is the structure of your import graph. Those import statements that create a source dependency between packages. In Go, your import graph must be acyclic. A package is not permitted to import itself, either directly or transitively, and a failure to respect this acyclic requirement is grounds for compilation failure. And more gravely, I think it represents a serious error in design. So all things being equal, the import graph of a well-designed Go program should be wide and relatively flat, rather than tall and narrow, with a lot of dependencies going lengthwise. So if you have a package whose function cannot operate without enlisting the aid of another package, that's perhaps a sign that the code is not well factored along package boundaries. If some code always needs to import another package for its types and to actually do its job, there's clearly a coupling there. So the dependency inversion principle encourages you to push the responsibility for the specifics, the concretions, as high up in your import graph as possible, and to leave the low-level code at the bottom of your dealing only with abstractions, through interfaces. Now, each of these 5 solid principles are strong ideas in their own right, but taken together they have a single theme. Martin observed that all 5 of the solid principles relate to the management of dependencies between software units. The dependencies between functions, dependencies between types, and dependencies between packages. And this is another way of just saying decoupling, which is indeed the goal, because software that is loosely coupled is software that's going to be easier to change. The single responsibility principle encourages you to structure your functions, types, and methods of a Go program into packages, and those packages should exhibit natural cohesion. The types should belong together. All the functions should serve a single purpose. Open close encourages you to compose types through embedding, rather than to extend them through inheritance. The Liskov substitution principle encourages you to express dependencies between your packages in terms of interfaces, not concrete types. And by defining small interfaces, we can be more confident that the implementations will faithfully satisfy that contract because it's a much smaller contract to satisfy. Interface segregation takes this idea further and encourages you to define functions and methods that depend only on the behavior that they need. And if your function requires only a parameter with a single interface method, then it's more likely that that function is going to have a single responsibility. And the dependency inversion principle encourages you to refactor the number of things that your package depends on at compile time. And again, we really see this as a reduction in the number of import statements in a package. So, in conclusion, Sandy Metz noted last year that design is the art of arranging code that needs to work today and needs to be easy to change forever. And if you were to summarize this talk, it would probably be that interfaces are the key here to applying the solid principles to Go programs. Interfaces let Go programmers describe what their package provides, not how it does it. And interfaces are really the unifying force in Go. They are the means of describing the behavior. And this shouldn't really be a surprise, as Go's interfaces provide the language with polymorphism. And polymorphism really is at the core of object-oriented design. Thank you very much for listening.